Okay, one thing about our equation here, either one of these, the electric field is directly related to the change in potential. This equation doesn't tell us the value of the potential at any one given point. It only tells us the difference in potential between 2 points, which is usually sufficient for what we need. But if we want to find the potential at a specific point, we need to know the value of the potential at another point in order to do this. Because remember, delta V is V final minus V initial. You need to know one of them in order to figure out what the other one is.
So that dr, if we substitute the electric field equation in there, we can just use r as our variable integration.
As long as you know the equation that describes the electric field, and yes, you can use r to represent how far away you are. This r would be the same thing, and you can integrate with respect to r. Yes.
So just if we had 2 point charges and we wanted to find out what the voltage difference was between the two.
That would be a little harder because you would need to know the equation that describes the total electric field, which if you have 2 point charges, that's going to be varying because the distance between them is varying. Mm-hmm. The easiest way to do that for a point charge is to integrate it and find delta V for just one alone, and then combine them. So negative integral for a point charge, we have kq over r squared.
I provided a good segue. I'm not doing this.
No, it's fine. It's fine. So our electric field due to a single point charge is kq over r squared times dr. Now, we're implying that dr is radially outwards, because this r is radially outwards. So by not writing it as a dot product, we're implying they're in the same direction. So delta V will be negative. K is a constant, Q is a constant. Integral of 1 over r squared is negative 1 over r. So the negative signs cancel. So delta V is K Q over r final minus K Q over r initial. Now, to know the value at a given point, we need to know the value at another point, because delta V represents V final minus V initial. If we know one of them, we can easily find the other. Electric potential. Any charge placed at an electric potential is going to feel a force, it's going to have some energy, it's going to want to move. How far away? Well, let's say this is our big Q creating the electric field, which in turn is also creating the electric potential. If I place a Q naught really close, I know the energy is going to be big. As I get farther and farther away, the potential energy is going to decrease, and that's because the electric potential is decreasing. If I get infinitely far away, if I make either R initial or R final infinity, let's say we started out infinitely far away, what would you expect the potential to be if you're infinitely far away from this charge? So, if R initial is infinity, anything over infinity goes to 0. The potential is going to be 0 infinitely far away. So that tells us the potential at any final point that's not infinitely far away is equal to K Q over R final. So the electric potential around any point charge depends upon the charge itself and how far away from the charge you're interested in. So now, taking this one step further, if I have two charges, if V, the potential, is kq over r for one of them, then the potential for both of them would simply be the sum of each of their potentials. So if we wanted to know the electric potential there, call this R1 and Q1, call this R2 and Q2. The total potential at that point will simply be K Q1 over R1 plus K Q2 over R2. And we're good. So it's easier in this case to find the equation that works for potential for one and then just apply it to multiple. Now, of course, now that we've actually integrated and found the potential for a point charge, you don't have to integrate again if you have a point charge. You can use the result we came up with. That equation will work as well outside of any sphere. And that's because this equation worked outside of any sphere. So basically, if you want to find the potential or potential difference anywhere, either you need to know the electric field, the equation for the electric field around that object, and integrate it. Or we can do similar to what we did with electric fields. For example, if I have a line of charge, and I want to know the field somewhere, call this distance A, this distance L. Rod has a total charge Q. If we wanted to find the electric potential, say at the origin, we have two approaches. This equation works fabulously if you know the equation that describes the electric field at that point. Which we've derived the equation that describes the electric field at that point. But we can also find the potential at a given point by treating our object as a whole bunch of little point charges and summing up each of their contributions to the electric field at that, to the potential at that point. So the approach for this one, the top equation would require us to find the equation for the electric field first, and then integrate it again to find the potential difference. This one's going to take a little bit more work in this specific example. If you have the equation for electric field, this top way is a great way to go. If you don't easily know what the equation for the electric field is, then I would treat it as a whole bunch of point charges. Nice thing is, this time, all you need to figure out is what dq is and what r is. And it's the same as it was before. dq is still going to be q over L times dx in this case, since we're along the x-axis. So that's still perfectly valid. R is the distance from whatever piece of charge you're looking at to the point you're interested in. So in this case, R is equal to x. So the electric potential at that point, in place of dq, we're going to put q over L dx. In place of r, we're going to put x. Our limits of integration, again, tell us where the boundaries of the charge are. So the left end of the rod is at A, the right end of the rod is at A plus L. The K, the Q over L come out. So we're left with the integral of 1 over x dx. So the natural log, plugging in the top limit first, minus plugging in the lower limit. This is the same thing natural log of anything minus the natural log of anything else is that first quantity over the second quantity. So that would be our potential at the origin. That, of course, this equation assumes the potential to be 0 out at infinity, because that's what we assumed to come up with this equation, and that's what we're working with. That is a perfectly valid assumption.
Okay, so that's, because the voltage is in relation to 2 points, right?
Voltage by itself is just 1 point.
Okay.
Delta V
Oh,
is relation between 2 points. But we derived that equation from this one by assuming that the voltage was 0 out at r is infinity. And that's how we came up with the value for V at a given point. So V by itself is the potential at one specific point. Delta V is the difference between 2 points.
Is there anywhere that assumption falls apart?
That
Is it if it's
where the potential is not 0 at infinity? None that we'll look at. What will be different if we wanted to know the potential up here?
on a nanosecond. Everything's
So if we wanted the potential up at a point some distance y, what will be different? All we need to know is what dq is and what r is. Still in the x direction, so dq is still q over L dx. Is r still x? R, that hypotenuse, this is r, will be the square root of x squared plus y squared, where y is a constant. The fantastic thing about potential is it's not a vector. There's no such thing as x or y components of potential. Potential does not have components. It's just a number. All you have is dq and r, and you're good to go. Our integral is dark colored. There's our integral. The k, the q, and the l come out. Integral of 1 over x squared, the square root of x squared plus y squared, is one of those that's on the test notes. It's the natural log of something. I don't remember what it is off the top of my head. But there's no components. It makes it infinitely easier. So for a point charge, we can simply use kq over r. For a line of charge, you can treat it as a whole bunch of point charges and integrate to find the total. For anything else, like spheres, cylinders, plates, etc., it's going to be easier to find it this way. Because the electric field's not hard to find around those objects. In fact, we have equations for the electric field around many of these. So it'll be easy to find the delta V by integrating whatever their electric field happens to be.
That be setting E times A is equal to your formula. Is that how you would find E?
That's how you find E, yeah, using Gauss's law. Okay.